So we have a second distinguished speaker, Yibo Zhu. Yibo is the CTO of StepFun. One of these very promising large language model startup in China. And before that, he actually worked in companies, big companies, Microsoft, Google, and ByteDance. And he started his career in Microsoft Research, and he did a number of very good work on RDMA, and probably especially the work that the DCQCN, which has won the Test-of-Time Award CTO last year. Let's welcome Yibo.
Okay, thanks for the introduction. I'm very happy to be here today, and yeah, very good to see good friends here. As Quinn mentioned, I got Test-of-Time Award last year, and in fact, I didn't go. But today I come here to give this talk that I value APNet more than SIGCOMM'. All right. So StepFun is a foundation model company in China. I was the co-founder of it. But today I will combine with our experience and innovation we've made along these 3 years. I will go over 3 projects basically. So some of you may probably already know about them, but I will talk about behind the scenes stories and also the challenges to deploy them in practice. So the first 2 are about large language model inference itself, 2 disaggregation techniques, and in the end, I will talk about basically, in the end, you will see how they are connected. So the last project was will be about high bandwidth domain that we design as early attempts to facilitate disaggregation in large language model inference. All right. So let's start from the background. So many of you probably know LLM is moving very fast. In the beginning, OpenAI actually laid out like 5 levels of AI, from chatbot to reasoning to agent, etc. And right now we're in the so-called agent era. The most popular apps are like Cloud Code, Codex, and also Hermes and like OpenClaw, etc. So StepFun also build models along the way from chatbot step 1 to now step 3.5 Flash series. And actually in March this year, we ranked #1 usage for OpenClaw, popular agent application globally. In the last few months, we have seen token consumption has been skyrocketing. So technical reason is that we have this so-called test time scaling, which means you let the model run for longer time, generate more tokens. It can solve more complicated tasks. A more complicated task can unlock more use case scenarios. So we basically have a compound effect. More difficult tasks, more tokens, more tasks. So basically in the last 1 year, I took a screenshot from OpenRouter. So we have seen like more than 10 times token consumption growing in 1 year. All right. And by the way, in March, we are like #2, I'm #2, and even today we are like in top 10. OpenClaw is just a small portion of the total token consumption worldwide, but it's representative. So, but on the other hand, there's not that promising fact, which is AI compute capacity. Although the whole world, including NVIDIA and also other Chinese chip vendors, are trying to build more AI compute, but it's on a slower rocket. It's still growing very fast, but it's much slower than the token requirement or token demands, right? So this picture I took from Epoch AI, I think it's a US media. It says 3.7 times of AI compute is built in the last 1 year. So it's much lower than the 10x of token consumption. And in US media, China is not like the rest of the world. So I brought a dot from the Chinese government data. So again, it's like 2 times to 3 times growing in 1 year. It's still much slower than the token consumption. So, in a very short summary, we must optimize large language model inference infrastructure to squeeze out more tokens per GPU. All right, so I think it's uh, everybody agrees with that. All right, so I will start with the first project, DCQCN. So we're StepFun, working with Peking University and UCSD to we were among the first to propose this architecture. So the story begins from 2023. So as our first trial, we were a very new company, right? So we want to build an app, and we build an app called Mobile AI. It's continuous, it's not important, but it's a role-playing app. So basically, you can chat with different AI characters on the app. So for the users to have a good experience, the product manager basically required that when we get this online, the user should get replies. Users say hello, and the AI reply should reply in 1 second. And also, when after the first word, the following word, the subsequent word, the generation should be faster than human can read, right? So we can translate these two requirements into technical terms. Basically, it's time to first token, also time per output token afterwards. At that time, we find it's a very challenging task to accomplish because there's one challenge is that for the AI role-playing app, so creators often write a very long prompt saying, "Hey, this character has this background. When it replies, it should reply in what style, in what length, etc." Also, like other characters, this role may know about. So all this information, it can be very long, like thousands of words, tens of thousands of words. So when a user enter a new conversation with this character, the AI model needs to process this prompt. And we all know that we can't dedicate one GPU for one user. So GPUs are shared among users. So when the other user is chatting with this model, maybe in a second round, but there's a new user coming in and there's a new long prompt process, it will interrupt the other user's experience, and it becomes very bad, and we can't really hold the SLO, which means like when we generate tokens, we need to be faster than human can read. So users may see very large interrupt for a few seconds because the GPUs are busy on processing the other prompt. So here is a very basic knowledge about inference, just in case you don't know. So there are two phases, as I just described. One is prefill. Prefill is basically process the input, the prompts, and generate KB caches. And the other phase is decoding. I assume most of you already know that. And so the prefill speed determines time to first token, while the decode speed is based on output speed. So these are two separate SLOs we need to satisfy. And another factor is that the prefill is more compute bound, because we just need to access the model parameters for once to process all the input tokens, maybe it's 1,000 or 10,000. But for decoding, for every generation token, I need to go through the parameters once. So the decoding is more memory bandwidth bound. So now, of course, the rest is history. A very natural idea is to isolate prefill and decode to certify SSO. So today it sounds so natural, it's so trivial. But at that time, like very few people thought about that, and there was also debate about that. I will talk about it later. But I can finish the design in one page. It's so simple. You just have a pool of prefill resources, a pool of decoding resources, and of course in KV cache we need to transfer from prefill to decode instances through RDMA network, and there's a controller doing load balancing, right? And this work is done with UCSD and Peking University. Of course, there are some detailed designs, and I won't go over that. But the evaluation shows very promising results. Right? For example, if I just have one GPU and I take all the online traces to generate requests to this GPU instance, assume it does prefill and decode together. So the x-axis is the request rate, and the y-axis is basically the latency. The latency for first token or the following tokens. Of course, you will see the faster request rate, the latency will go up. And if we take SLO to bound the request rate, and we basically have to take the minimum of prefill and decode requests per second. And this is the number we get. But if we But alternatively, if we do prefill, if we deploy this serve, for example, if we have two GPUs for prefill, one GPU for decode, and it works separately, in the end, we will get much higher requests per second per GPU and satisfy the SLO. All right, so today, even I think almost all the inference service providers deploy this solution. But at that time, I can tell you when sorry, what? Okay. At that time, we were actually challenged or let's say, so when we submit this paper to OSDI, the reviewer didn't give a high score. Although maybe it's the most cited paper from that year's OSDI, but the main reason is that there's a related work published earlier. It's called trunk prefill. Okay, the trunk prefill, the idea is that when I have a very long prefill, so I can split into multiple chunks, smaller chunks, and I interleave or batch this trunked prefill with decoding requests. So the decoding, the output token of the other user won't be interrupted too much. You can still generate a little bit, right, along the way of prefill. So so it basically, and the reviewers will point to this work, say, hey, this work already solved the SLO challenge you raised, etc., etc. And also because it's easier to implement, you can just implement on just one GPU, right? And there's no communication needed, no network issues. And it's also merged into like a VRM, like inference framework earlier than us. So yeah, so that was the questions raised. And in fact, objectively, it delayed the adoption of PD desegregation. But in the end, today everybody still uses the PD desegregation. So so my take is that desegregation is more fundamental because you do have two phases of compute. They have very fundamental different properties and requirements. And it's best, also SLOs, right? SLOs are also very different. It's the best to isolate them, and it's the best to put them on different resources. And once the engineering gets matured, the more fundamental solution will win in the end. So in the past slide, I actually, if you notice, I mostly talk about SLOs, how we can satisfy SLO and isolate them to meet them. But in fact, there's another additional gain from PD desegregation, is that it provides the possibility to use heterogeneous GPUs for prefill and decode. Okay, this is because for different GPUs, they provide different values on different resources. Some GPUs provide better value for compute flops. some GPUs provide better value for memory bandwidth. As I said before, prefill and decode require one is more compute bound, the other is more memory bandwidth bound. So that means if I know the model, model architecture, I know the flops it take for prefill, I know the memory bandwidth requirement for decode, and I know the app, like the average input length, average output length, I can calculate the ratio of the prefill and decode, and I can put different kinds of GPU resources to serve them, right? And the optimal setup is absolutely better than if you use 100% this kind of card or 100% that kind of card. So a mix is actually better, right? But the problem, the challenge of this is, it depends, right? It depends on the model and the app. So if the model changes or the app changes, the ratio can change. And it becomes a very big challenge. So that's the reason why, although this is the additional gain from PD disaggregation, much fewer company actually does it for heterogeneous GPUs. A lot of companies today still use homogeneous GPUs for this, but not heterogeneous. So if we think about it, I can see there's a big mismatch between the models and apps, also the hardware and clusters. They change on very different frequency. For every month, we see new models, new apps in the AI world, right? But for hardware cluster, it takes years to change. And that means there's a tussle between software developers and also and the hardware developers. So on the software side, we want to lower the cost immediately for this model, because next month it can be next model, next app. But lowest cost, the optimal ratio of the resources, if we want to go with the heterogeneous route, it depends. It requires a custom tailor-made heterogeneous cluster, right? But on the hardware side, the hardware people will think about it. So it takes us months or year to build a cluster. And if I take just today's model app to tailor-make this cluster, by the time I finish, it's 100% out of dated. And how long will it last? How long will the design last? So I can the only middle ground I can see is that if we can have a network or evolvable, scalable network to solve it, and with this network we can build a mixed use. The mixed use is the keyword. The mixed use cluster. So different workloads, different apps, different models can run on them. It's very similar to cloud, right? And today, I know who actually deploy large-scale heterogeneous PD disaggregation. Some of them are actually cloud companies. Okay, they have this large enough cluster, and they can adapt to different changes from the models and apps. They can multiplexing, right, from these different customers or multi-tenants. If I have just a very, very, very small deployment, tailor-made this deployment, I cannot adapt, right? Once the optimal ratio changes, I cannot adapt. So let's take that in mind, but I will then move on to another disaggregation, which is the more advanced one. It's attention FFN disaggregation. For this inference process, now I want to zoom into the decoding phase. Why? Because decoding phase, as I said before, is more memory bounded, which translate to lower flops utilization, which translate to lower GPU utilization. Okay, so it basically is more expensive than prefill, and it means there's more room to optimize. For decoding, I think I said before, for every generated tokens, I have to go through all the parameters once. And that includes two major parts in today's large language models. One is attention, the other is called FFN, or feed forward network. So on the left is a very basic architecture. And to reduce the cost of memory access, batching is the most important technique, or most basic technique. Because if I batch multiple requests together, for example, if I batch 10 tokens together, then I can just generate one token, 10 tokens with just one access of the parameters. Okay, so then the memory access cost is amortized. However, the attention part and FFM parts behaves very different with batching. So let me elaborate. I take this picture from UCSD. So our friend Hao, they write a very good blog about this technique. So so let's start from attention. So what attention does in decoding is basically it needs access all the KV cache of previous tokens and then generate one token at each round. So if we batch multiple requests together, you will find it doesn't really make your KV cache access more efficient. Because if you batch 10 requests together, you need to access the KV of 10 sequence. Okay, so it doesn't really improve the flops utilization. 10x batching means 10x memory access. Okay. And the more batch, the larger batch, it actually require you to have larger memory capacity to hold the cache in the GPU memory. So it's actually a bit negative for attention regarding batching. But for FFN, it's a logic I talk about before. So you can basically if I batch 10 sequence together, I can just read the memory once and then generate 10 tokens. All right, so FFN loves batching. So because of this, again, so it's very similar to prefill and decode. So now attention FFN on decoding has two fundamental different computation requirement or properties. So a very natural idea is to separate them into two different resources. Okay, and then use network to do communication. Okay. Still, I say it's very natural, and but this idea today is still very debatable. Okay, there are still very many people arguing, hey, we shouldn't do this because 1, 2, 3, etc. But just like PDD segregation, I personally believe fundamentally this is the better way to do. Also, this year, if you notice, NVIDIA Jensen Huang also proposed this architecture with two, GPU and LPU, two different kinds of AI chips to do this architecture. But anyway, so last year we were also one of the first to propose this architecture. So we have FFN instance, attention instance, and then network between them to communicate the intermediate activations. And of course, if you do it right, you will see performance gains. Even on homogeneous GPU, homogeneous setup, like I think on the left, is from UCSD. So they use NVL 72 is a GB200 cluster. So it's a homogeneous setup, homogeneous GPUs. But because you can use different batching strategy for attention and FFN, then you can actually get performance gains. And on the right side is what we come up with theoretically. If you use different kinds of GPUs, different heterogeneous GPUs or AFD, there's even more performance gains. So I mean the reason is very obvious. You have two fundamentally different portion of the network. So again, I say this is debatable because very few companies deploy this right now, and and I took the same page. Basically, it's exactly the same page from PD disaggregation, right? It's still the same problem. So we have this theoretically very good technique called disaggregation. We want to place different GPUs for different compute, but the optimal ratio of the hardware cluster it's very hard to decide. And the only solution is to build a large enough mixed-use cluster. Here, for FD actually has a bigger challenge on networking than prefill decode disaggregation, which is which is a bandwidth requirement. Because for prefill decode disaggregation, the transmission is per request. Now for this AFD, because the model will have tens of layers of attention and FFN, so it means every layer need to do this communication between the two parts. All right, so in short, I think from the last two projects, they are actually motivation for my talk today. Is that we actually need a new generation of network to facilitate disaggregation. Disaggregation is really good because for squeeze out more tokens, like pursue the extreme efficiency for inference. Okay, so it requires first the network must be scalable, and flexible and evolvable. Also, it needs high bandwidth. This is a major difference from today's RDMA network. It needs terabytes per second per GPU bandwidth, and also very low latency. And it should also be general for different GPU chips and be fault tolerant. Today we don't have this kind of network. We basically have 2 out of 3, right? If we talk about RDMA network or Ethernet network, we don't have that kind of high bandwidth, like terabytes per second per GPU. We only have terabits per second. All right, so but if we talk about NVLink, NVLink has the bandwidth, but it's not scalable. So today we don't have this kind of network. So that's why I will talk about the last project is a very early attempt to build such a network. But I don't think this is the final answer. It's still a very early research prototype. But our goal is clear. We want to have all 3 properties from the network so that we can do better disaggregation. Okay, so let me go over the existing high bandwidth domains or NVLinks, right? So today's designs can be categorized into 3 types. First is switch centric, is the NVL, basically NVLink, and people know more about TPU. So TPU is actually like a hybrid, but a more pure solution is like a GPU centric. So there's no switch. You just interconnect the GPUs with some kind of topology. All right. And TPU is a hybrid, means it connects the GPUs as well as there are switches. All right. So I will go over with the first 2. So you know the pros and cons of them. For the switch centric, this is you can view it as the upgraded version of Ethernet, right? So you basically build a closed topology. You have switches, and it provides any-to-any high performance communication, and that's the good thing. But the problem is it's very high cost because you need 10 times of the Ethernet bandwidth, and the very naive way is you have 10 cables per GPU and then 10 ports, right? And for even for very small network, so if you look at NVL 36, you can imagine the switch capacity needs to match 3600, something like that. Sorry, so 360, something like that scale. So the cost is high and the scalability is low. Also, there's a resource fragmentation problem because the scale is small. Let's say you have 36 GPUs connected together. But if I say I want to do EP16 or TP16 per instance, then you will have 4 left unusable. So fragmentation means waste of resources. And then there's bad fault tolerance because once the switch goes down, you will have bandwidth degradation. Another type is GPU-centric HBD, high bandwidth domains. The good thing is about it has low cost and it's high scalability. Because it doesn't have switches, right? I can just connect them in the ring, and the ring can be arbitrarily large, right? And no switch is required, so the cost is low. But the problem is it has low any-to-any communication performance, right? If I go with the node from the upper left to the bottom right, I need to go half of a ring to reach that. So the any-to-any communication will suffer from that. Also, it has a very large explosion radius. Because imagine if you have one server goes down, then the ring breaks. All right. If you keep using it, you will become a line, not a ring, right? So you will basically have half of the bandwidth. So if explosion radius is really large. And for hybrid designs, it's basically both of it's a bit of both, right? It's in the middle. For brevity, I won't go over that. So our solution is it's a new type of high bandwidth domain. So we use a new type of a transceiver device to overcome the challenge of the both solutions. So I will go over with the first two designs. First, we have this optical circuit switch transceiver. So it's a very light. It's like we change it from a module, a light module, optical module to optical switch. So it basically has an 800 gigabits for transceiver and but the good property of it is that it can change the path, it can change the topology. So a little transceiver can connect to two GPUs and have two external paths, but they are not active together. We can switch between them. Okay, and the switching has very low latency. And with this transceiver, we can connect the nodes or GPUs into a K-hop ring. Now, if you remember the drawbacks of ring topology I just showed, the common one, if there's a node fails, the ring breaks into a line. But with this optical switch transceiver, we can change the topology, like from 1 to 2, 2 to 3, to skip node 2 to directly connect 1 and 3. So this is the advantage of optical circuit switch. So then with this technique, we have the advantage of both worlds. So this ring or this topology can scale arbitrarily large. You can scale to data center wide, and the explosion radius is very small. So one server down, I can still maintain the whole ring topology. All right. So that's an evaluation about the fault resilience. I don't know whether you can see very clearly, but we take the trace from our production, basically which server goes down, which server needs to get repaired, etc. And we put it into this simulation and see different kinds of topology, including NVLink, including TPU, etc. Which one has is more fault tolerant? And if you can see the infinite band, our solution is at the bottom. It's basically the GPU waste ratio is very low because it's node level explosion radius, right? One node goes down, just one node goes down. It doesn't bring other nodes down. All right, so if we look at the comparison is the way the GPU weight ratio is 10 times to 20 times lower than existing solutions. And the cost is also the lowest because it doesn't have switches. It doesn't have like 100 port switches, right? You just connect all the GPUs all together, etc. And as I said, this is still a prototype in the lab, but all in all, what I want to say today is that it's very important to optimize large language model inference. And I truly believe in disaggregation. I believe if you have multiple different, fundamentally different portions of a compute, you better split them, isolate them, but at the cost of networking. And that's why we need next generation networks. High bandwidth domain is the way to go, but it's not scalable right now. We need to make it more scalable, make it more fault tolerant, of course, with affordable cost. Okay, that concludes my talk. Thanks.
Yeah, thanks, sir. For the talk. Yeah. Well, I'm sorry. Yeah.
Hello, Morgan from Shanghai University. Great talk. I have one question. Is that you say any is very costly in ring style network. So how does the ability to overcome this question?
Yeah, so basically it has the similar challenge as the ring topology, but we can compare with ring. We can do more things, it's including the paper. So basically, we can do 2D ring, 3D torus, just like TPU does. Okay, so it's not as good as fully switch connected networks that can't be. But I mean, there's still middle ground you can play with.
Okay.
And yeah, but with TPU architecture, for example, it does 4x4x4 3D torus, which means 64 cube nodes as a cube. And in that case, the explosion radius is 64. So one node goes down, 64 nodes goes down. But our hope is that with this kind of optical circuit switch, you don't have that problem. Okay.
Thank you.
Okay, Yibo, very, very excellent talk. I also appreciate that you value this more than SIGCOMM'. Yes. Also, I value your very much, especially actually your first two, right? Computer code disaggregation and tension FFN disaggregation. So when I you talked introduce these two work together, actually for me to report a very important principle in computer architecture. I quickly opened that book and find that there's actually there are eight great ideas in computer architecture. I'm not sure if you when you design this work you can come across that. It says performance through pipeline and parallelism, right?
Mm-hmm.
I think this fine-grained disaggregation will feel equal, and then in the code, you have attention and event. So basically, you divide this whole process into different stages, so that you can do better pipeline and parallelism. Right?
Yeah,
different use suitable divided resources. I think that should match that principle.
Yes, thanks
I'm not sure if you thought about it that way.
Yes, thanks for the comment. So honestly, I would say my main motivation is divide and conquer. So basically, divide and conquer, and then better pipeline. I think better pipeline is essential for this kind of work. For all kinds of disaggregation, if you don't pipeline, then the network will eat you. Right. Yeah. Okay. So I would say yes.
Right.
Yeah.
So I think there may be different ways on that. Is essentially behind the scene. I think there should be a lot of work share the same principle to come back to very fundamental
Right.
software designs. So you also mentioned that this attention and still haven't converged. So the industry haven't
Right.
completely apply or adopt it yet. Right? So you said maybe some concern debate still behind the scene. So can you elaborate a bit more on this? So this is archive paper or is published or it's just
No, it's not published. It's not like an academic paper, but it's a tech report.
What's the concern the debate still on this this location? Can you say a little more on this?
Right. So one problem is still the engineering capacity. Just like the early days of PD desegregation, the software is not that mature. And as you just mentioned, if you want to get good performance, you need to build a very good pipeline. And you need to balance attention compute, communication, and FFN compute, and build a good pipeline. And that pipeline building is not that easy, as I would say. If you have online requests, different bursts of requests coming in, short and long context requests. So there is some engineering work to do. That's one thing. Another thing is to get bigger gain, you need to have heterogeneous chips for attention and FFN, and then that goes to this challenge. So if you want some, first you need to have two very different types of chips. So GPU may be one good type for attention, it's very good, but for FFN, maybe you need LPU like Grok or other type of chips to have different enough property than GPU. And then you need to interconnect them together. All right. Even NVIDIA has GPU and LPU, but the NVLink hasn't covered both of them. So now today, if you want to connect GPU and LPU, you go through Rocky, you go through RDMA. And Ethernet is still fast enough for this type of communication. I would say we hope it can be 10 times faster, I would say. Yeah.
I have a follow-up question. So it's very important for India. So regarding these very realistic concrete challenges or optimizations you have done and you came across. So what are these challenges that belong to, for example, the China-specific problem as this chips, the power of the chip, or what are the international problems that even in NVIDIA is very high density computing power?
Yeah, it's nothing about like geopolitical issue or Chinese.
No, it's not. It's not geopolitical issue, but you have in China you have this clusters with like a bit low on and then those.
I'm not saying that. So fundamentally there are different types of chips.
Yes.
And more concretely, you have different medium for the storage. So actually you have HBM, you have SRAM, you have DRAM, and they have different capacity and bandwidth and cost. Okay, so basically GPU today, H200 or B300, they use HBMs, and they represent bandwidth to cost ratio. And if you talk about LPU use SRAM as the storage medium, and then the bandwidth is much higher if you consider it by for example the capacity or the computation power is lower. So fundamentally, it's basically different chips. Different chips has different properties. They fit different, attention of different portions of the model.
So they're still valid.
Yeah.